早晨，早晨。Testing. 1, 2, 3, testing. Hello. Good. Angyu, can you hear me? Just checking.
Yes.
Okay, good. Thank you. So I guess we can start by having a question. You have any question at the moment? If no, then let's first begin by reviewing what we covered in the first class, and then go ahead. The plan of today is to try to complete the theory section of the descriptive statistics, and we will see whether we cover the Excel and R in the lab section or we do in the class. I would see if is it convenient for you to bring laptop. It seems like everyone bring the laptop, but it's not clear for me. But maybe we will cover the theory in the next class first, because I guess may not everyone want to bring their own computer to the school. We will see. But let's begin the class. Okay. So let's very quickly review what we have done in the last lecture. In the last lecture, we give an overview of statistics, which is two parts. We have descriptive statistics and inferential statistics. And basically, this class is divided to half, and where the first half will be descriptive and the second half will be inferential statistics. And let me close the door, I guess we should. And the second part, look at data, two types of data. One is categorical, one is numerical. And we know that, I mean, the first type of data is very different from the second one, and the tools required are very different. But nevertheless, our class will be focusing ourselves on the numerical data, okay, mainly, okay? When we do ANOVA, we talk about some categorical data to divide the data into different groups. But other than that, we are concerned ourselves with numerical data, okay? So that's the idea. And for visual representation, have I shared the screen? Oh yeah, haven't. So for visual representation, and then we said we don't want to engage ourselves discussion right now, which we will be talking them in the we'll talk about Excel and R, and actually we will talk about those issues. Okay, and we just mentioned in the class there are 3 ways to represent data. Okay, one is called central tendency, which is we try to use a single number to represent the whole data set, okay, that we have learned is mean, median, and mode. And the second one is dispersion, which is a number again to tell us whether the central tendency would make a lot of sense, okay, whether sensible or not, okay, because of the fact that 2 different data sets can have the same central tendency measure, mean, median, mode, but the accuracy of these measure varies, right? Because it's the more data that condensed to the mean, right, is more representative of what the mean means, okay? And dispersion is the way to handle it. The third one is shape, okay, shape. So we want to know 2 things. Actually, there are many ways you can measure, but 2 different ways to look at the skewness and kurtosis. Okay, skewness actually means whether the data is more likely to concentrate on the left side of the mean or right side of the mean. Okay, and you may ask why we care about that, and because we only know mean, but we really want to know whether it's concentrated on the left-hand side, most of people, or right-hand side. The reason is like, say, look at the application, look at, say, income. You want to see on average, is it more people are earning more than the mean or less than the mean, right? In terms of the society, the government, you want to help the poor. You want to see it's actually, it's a lot of people are poor, right? Maybe actually it's a lot of people are well above the average. That should be fine. But if there are a lot of poor people, which is way below the median, then it's not so good, okay? In terms of business application, you can imagine that you are a hotel manager, say, or a shop owner. You look at the how much they spend on your shop, right? Look at the mean data, okay, tell you how much they spend. Look at the dispersion data, say range, interquartile range, variance, which we cover today. And then you see how accurate the mean is, right? And the next question would want to ask is, okay, I know the mean is such and such and such, and you want to do advertising or do some marketing campaign, and then you want to target which customer, right? If the skewness tell you is like a lot of customer is on the lower end, right? So then you should price a new product or focusing or advertising strategy on lower end, right? If a lot of people actually is a high-end customer you have, right? Then you probably would tailor your product or tailor your advertising campaign on those customers. So that is why we care about the shape. And the other one is called kurtosis, right? Kurtosis is, as we said, it will be looking at the fat with the tail distribution, okay? Whether the two ends, at the extreme two ends, how is it large or small, right? And in application, the law say in finance, look at the extreme risk, right? Or catastrophic risk. So we want to see how likely that certain rare event may happen, okay? So if you are modeling a financial product, you really want to see if your product is actually, your modeling should have a right kurtosis, right? As I said in the last class, right? Some people said it's the 2007, the financial crisis is due to the wrong modeling that ignore the kurtosis, right? If for those of you who are doing insurance or actuarial science or other modeling, then they know those catastrophic events have to be taken care of, right? We know these days a lot of event goes on, right? Like COVID is actually a very extreme rare event, and also the flooding in China, right? Zhangzhou is a very rare event too, and these days a lot of rare event happens, so that's why you care about shape as well. So let's really very briefly talk about mean, median, mode again a little bit. Just try not to repeat too much, but just a little bit about the mean. Again, the formula is well known from your elementary school, which is sum of all the observations, and that is you divide by the total number of observations, okay? And the formula have no problem, of course you don't. I think the key is to understand the meaning of this equation, which effectively means that it is at the center of data in the sense that the distance, okay, on the left of the mean to each observation is equal to sum of the distance to the right to the mean, okay? That is the meaning of the center of data. So that's why it calls center of tendency measure. It's measuring center of data using a distance idea, okay? So if you observation, you move a little bit, the mean will move because talking about the distance, okay? In such, it means that you will be affected by outlier, okay? If one observation is extremely large, okay? Because we're calculating distance, then we move a lot, right? So remember the example we have is, say this is the income data, looking at the 5 people, right? The mean will be 3, right? And this case, mean will be 12, right? So go back to the example of a shop owner, right? If your data is actually this 1, 2, 3, 4, 5, then actually you can look at, suppose this data is how much they spend in your shop, right? Then in that case, you would looking at the 3 is a representative idea, then you can try to boost the sales, try to design a campaign for assuming that they are spending $3 in your shop, right? And instead you collect data like in this way, right? The mean is not that useful because you're thinking that actually on average they're spending $12 in your shop, for example. Then you may try to sell them, say, $10 object, right? Actually would not be, no one would buying except probably the last guy, right? So probably you have to figure out more carefully. So that's why later we learn about why we care about the median, why we care about variance, right? So that is the idea. Okay, so we don't go to the technical thing. So median is also the center of data, but you don't care about how distance of the data, right? Just exactly center of data. Okay, you sort them up and exactly the middle one. And if the data is odd number, they exist exactly the middle one, right? Suppose you consider data, you have 3 observations, right? The second observation is exactly middle. You have 5 observations, right? The third one is the middle because 2 on the left, 2 on the right. If you have 7, again, will be the 4th one is the center because 3 on the left, 3 on the right. Okay, so there's odd one, there's no problem. That's exactly middle because n plus 1/2 is exactly the middle one. But what about even? Okay, whereas even is not that clear what is in the middle, right? Because suppose there are two observations, which one's the middle, right? You'll be halfway of the two observations. So as a compromise, then we'll use the mean of the two. So you can imagine this interpolation, right? It's exactly what you mean, right? It's like exactly what this would mean. Maybe this is exactly this guy. If you, so this is the K, right? This is n plus 1 over 2 lower bound, n plus 1 over 2 upper bound, xk. So it means that halfway is here, so we just do it this way. So because it's a similar triangle, halfway here is same as halfway there. But later when we talk about interquartile range, we'll give you a more detailed graph on this one. So don't worry about the drawing. If you can't see properly later, we'll talk about the interquartile range. This is the standard linear interpolation. So if you have, say, you have 4 observations, then you have is 2.5, right? Because 4 plus 1 is 5. 5 divided by 2 is 2.5. And 2.5 will be looking at half of the second observation and half of the third observation, right? And again, the same idea, you have 6 observations, right? You'll be 3 on the other side, 3 on the other, right? So will be 6 is 7 divided by 2 is 3.5. So it's 3 and 4 and a half of the midway between the third and the fourth observation. Okay, so just the example again, just make sure that you really got it. So 1, 2, 3, the middle one is 2. 1, 2, 3, 4, that will be, because for observation, 4 plus 1 is 5. 5 divided by 2 is 2.5. So it's basically the second and the third one. Okay, so average of that. And you can see the next one is, because we depend on order, so if you change the last number to humongous last number, doesn't really change the median. Okay, so that's a good point of median because of it didn't affected by the outlier, but also is also a matter of a drawback because it doesn't use up all the information available on data. Okay, so it's a good point, also a bad point. So that's why in looking at the data, you always reporting the both mean and median. Right? Look at the government data, look at the income from the census data. You always have the median and the mean at the same time. Okay, so it's not because of one of them better than the other, but you always need both of them to get a better, clear picture of those. But the next one is mole, right? The mole is you don't involve almost no calculation, right? You just look at the frequency table, look at those who appear the most with the mole, right? Of course, there's a drawback of this measure is like if one observation is just one less frequency than other, you just ignore it, right? Suppose the data is like one, maybe example like this, right? Say 1, 2, 3, 4, right? You get all of them, right? 1, 2, 2, 3, 3, 4, then you get 2 and 3 because only 2 and 3 appear twice. But when you have 1, 2, 2, 2, 3, 3, 4, then 3 is gone, right? And you can imagine that you have many 2 more, many 3 in this data, but only because 2 appear once more, then 3 disappear, right? So sometimes you don't really think that this is the best way, but this is the drawback of mole, but still we use it. And the good thing about this mole is it also applies to categorical data, right? We talk about gender, race, or likelihood scale, or many things. Mole can still be meaningful. Okay. So I think we have covered it. the free center tendency. Any question before we continue our? Sorry, I changed the mask because it's a bit. So, so dispersion. Last class we covered the range and IQR, part of the IQR. So after that we go to the variance, standard deviation, and coefficient variation. Okay, but let's start again with range. Range is very simple, just this biggest minus smallest. If the data is not ranked, if the data is sorted, then just the last observation minus the first observation is ascendingly sort. Okay. Again, that has the same favor of the idea of the mean. Okay, if the largest data is very large and the smallest very, very small, the range will basically overestimate the dispersion of data, right? Because you would be really expanding the scope, right? So, like this question, you have 1, 2, 3, 4, 5. The range is 4, but 1, 2, 3, 4, 50. The range is 49. But do note that actually the data itself here, most of them are concentrated in a single digit, but because of large observation is huge, the range swell a lot, right? So that's why range usually is not a good measure, but still give you something, right? Because sometimes when you care about extreme risk, right? As we said, the tail we care, then range is still a good thing to look at. So that's why we still talk about it. It's not something like I often said the drawback, but it's trying to tell you that the idea when you try to use some measure, there are always a drawback, okay? There's always good point and there's strong point and weak point. So that's why we talk about different measures of the same concept, right? So sometimes a mean, median, mode, then you have to usually report 3 of them. We try to see in which situation that will fit better, right? Same here, right? You should also try to report beside mean and median for the tendency when you try to report for the talk about the data that about the dispersion. You should talk about range and interquartile range. Both of them will be important, right? Because range will tell you that how extreme the data set is, right? Look at the smallest and the biggest, right? How big difference they are, right? I mean, we talk about, right, that was about, you read about the thing, right? Recently, I know many of you know in China, there's a, talk about the getting rich together, right? 共富裕. So in that case, 共同富裕. So that means that is a concept of talk about the range, right? And they talk about, some people talk about those actor and actress or KOL are earning too much money, right? They have some restriction on those money, right? And they compare those people who are not so rich, right? So poor, then they compare is talk about range, right? Look about the, and talk about, look at, remember in the, I think a few weeks ago, talk about the occupying the Wall Street, right? They talk about the 99% versus 1%, right? Talking about, that's about the range, right? Talking about how those rich people they are. So we talk about the range, not talk about interquartile range, because 1% will not be the in interquartile range, right? So range sometimes do have some important component there. So quartiles. So remember the tiles, right? Quartile, basically the data you will be at the end, right? You will be having a divided into different 4 parts, right? Right, this will be the quad data, right? And then we learned that actually is this is the range, right? And the interquartile range is this one, right? And we learned that This is the median, right? This is it. Median, and the median at the middle data, and we have Q1, right? And this is Q2, Q1, median is Q2, and the first Q3, right? So the distance, the purple arrow will be the one that we are measuring, okay? So the question is very straightforward, right? This is the how, if the data is very diverse, very dispersed, the purple one will be large, okay? And you can imagine that the red and the purple should be, most of the time you will see the data should be moving in the same direction, right? The more dispersed data, then the both of them, the measure. But as we mentioned, the red one, the range will be really affected by how extreme the last data is. So that's why it's not, can change very substantially, depending on how you collect the data, right? Suppose if you do random sampling, right, and then you try to ask how much people is earning, right? And then probably if you try to happen to go to the peak, right, then you get a very high number, right? But if you never go to the peak, then you never go to repulse bay, then probably you don't have the problem, right? But anyway, so IQR is this the third quartile minus the first quartile, okay? And you may immediately ask, right, why I divide them into 4 parts, right? Not 5 parts, 6 parts, 7 parts, and look at distance between here and there. Okay, definitely you can use it, but it is divided into 4 parts has a virtue of you can use median twice, right? In the old days, right? Find the median, everyone knows it, and look at the median, divide the data in 2 parts, find the median the first part and median second part, look at the difference. So in the old days, when you don't have computer, then that was something easy to do, right? And the old days, you don't have a lot of data anyway. But now you have a computer, right? We don't have to use IQR. We can look at the distance, look at how, depend on you, in the quartile, you divide them into 4 parts, right? Quartiles. You can divide them into 5 parts, 6 parts, 7 parts, 8 parts, and look at the difference. That's not a, that's no problem. And you can imagine that if you use the machine learning or use the data AI, they can look at those. So you need not restrict yourself to what we talk. We talk about is just a common example that to measure those ideas. So you can invent a way to do it, and indeed, those data science people actually invent some way to do it, right? In some problem, this measure is good. In another problem, the other measure is good, right? Also in the mean, we also mentioned about weighted average, geometric average, and harmonic average, right? So those are different ways to measure the same thing. So same here, okay? But let's go to here. Last time we talked about 1 and 2 method, and the third method we don't have time to cover. So let us repeat again how do we do the first method and second method, okay? First method and second method is basically the idea is median, using a median idea of median, okay? The first method is you look at the median first, okay? Look at the median data, okay? And you would include the median that we will take the first half of the data, find the median again. So that gives you Q1. Look at second half data. If the median happen to be in the data, you also include it in the second half, find the median. That will be the Q3. Take a difference between the two. That will be the method 1. And method 2 will be we're ignoring the median when you cut the data into 2 halves. Okay. So let me repeat the example again, because so we have 1, 2, 3, 4, 5. Okay. Method 1 was said, okay, first find the median. In that case, is 3. Why 3? Because we have 5 data point, n is 5, n plus 1 is 6. Okay, 6 divided by 2, which is 3. So the third data is the median. Okay, and which is number 3. And method one said you should include the median into your cutting, okay? The first half of data, which is 1, 2, 3, okay? And the median of this will be 2, right? Obviously. And this will Q1. And the median of the second half also include 3. Then it will be 4. And 4 minus 2 is 2, okay? And method 2 will be saying that, okay, when we do the cut the data in 2 halves, we shouldn't include median, okay? And in that case, remember median is 3 for the overall data. Then the first half become 1 and 2 only, because median is should not be included. And 1 and 2, the median of 1 and 2 is just because 2 data. So it's just mean of the first 2 observations, which is 1/2. Okay, so that's why Q1 is 1/2. And again, look at the second half data, right? Remember 3 is not included for the method 2. So 4 and 5, the median will be 4.5. Okay, because this is the average. So it's 4.5 minus 1.5, which is 3. Okay, so you can see that these 2 methods can give you different measure of IQR. Okay, and if you look at the menu, there's a, I think I told you, is that there's actually, look at this package, our package, or any other software package, at least there are 9 different ways to calculate quantiles. Okay, but this is the 2 way. Okay, and these 2 are different because it's odd number observation, right? Because when the odd number observation, the median is included, is exactly the middle data, right? When you have even number data, right, 1, 2, 3, 4, 5, 6, in that case, the median is not in the data set. It's not an observation. In that case, these 2 methods coincide, right? Because 1, 2, 3, 4, 5, 6, 6 observation, 6 plus 1 is 7, 7 divided by 2 is 3.5, and 3.5 is not exactly any number. So the median is 3.5, which is Q2, but when you calculate Q1 and Q2, method 1 method the same, because the first half is 1, 2, 3, because 3.5 is not there, so that's fine. And 4, 5, 6 doesn't really matter, you don't have 3.5, okay? So that means that method 1, method 2 will give you the same interquartile range, okay? So that's why when you look at the data, when someone tells you IQR, you have to know actually what they're talking about, okay? And now I tell you the third one, which is supposed to be more or less a default one. So you will see in Excel spreadsheet for R, sometimes they would be using somewhat similar, okay? With somewhat variant, but so this is the answer here, okay? So how do we calculate median, okay? The idea of Q1 and first quartile, second quartile is exactly what this definition said, okay? Is look at the n+1 over 4th, okay? Actually, it's coming from the idea median, right? Median is n+1 over 2, okay? Then I just extend this idea, exactly look at the 1/4 of n+1 rank and 3/4 of n+1 rank data, okay? So look at the data of this half of n+1, right? Remember what we do is in the median, look at the picture again, right? Is when n+1 over 2 is exactly integer, we don't have any problem, just pick up what we want, okay? But when you have n+1 over 2 is not integer, right? And you convert it to decimum places, right? The decimum point must be 0.5, right? Because it's not integer, must be 1 over 2, right? 1 over 2 must be 0.5, okay? 0.5, we would be what we are doing actually, why we're doing average of the 2, right? The idea is saying that this is xk, right? This is xk plus 1, right? And then we actually want to know xk plus 1/2, right? Want to know that particular point. So it will be halfway. So that's why we will be looking at average, because it's halfway from either side, right? Maybe I don't use, I use a less technical, don't use the K, maybe. So maybe I have data with 6 observation, right? Then maybe we will be 6 when n is 6, right? n plus 1 over 2 will be 3.5, right? So then we look at the x3 and x4, right? When we look at the median is x 3.5, okay? What is x 3.5? Don't exist, right? So we want 3.5. Actually, what we want is halfway from x3 and halfway from x4, okay? So that is the idea, right? So that's the halfway of this is we're doing a halfway, okay? So what about if we divide the data into a quarter divided by 4? So we will still have a chance of this number, or we have this number, or this number. Either is 3.25, 3.5, or 3.75, because you divide them into 4, and you convert it to the decimal places, it must be 0.25, 0.5, and 0.75. Okay, is that okay? Is that okay? This is something you learn from the elementary school. Okay, so what is the, how do you calculate data from 3.25, 3.5, 0.75? 3.5 you know, right? It's halfway. Okay, and if you want 3.25, right? In this one, right? So how you would calculate this one? Okay. So you would want to say proportional, right? So this is 0.25, okay? This is 0.75, right? It's up to 1. So that means that I want to have 0.25 of this whole distance, okay? So that's why this x 3 plus 0.25 times the whole distance, x4 minus x3. So that's how we get that equation there. Is suppose you get is 3.25. How do you calculate what is this exact number? You'll be the third one, okay, plus 0.25 of the distance, okay? And again, if you have 3.75 here, will be 3.75 x4 minus x3, okay? So that is the idea, is that it's 0.75 of this whole distance, okay? But I add this extra slide, which is not in your slide, but just to give you a better idea. So we will try to explain this formula by using what you learned in the high school. Is called the similar triangle idea, okay? So the x-axis is basically the k, okay, which is something you want to calculate. K, assume k is integer, right? K in this case is 3 or 4, okay? So you calculate p times n plus 1, right? Say suppose you calculate data is, in this case we have n is 6, okay? 6 plus 1 is 7, right? And 7 you divide it into p is quartile, right? Q1 is p is equal to 0.25, okay? It's 1/4, 0.25, okay? And it ends up that it will be somewhere in the middle. It's not integer, right? K and k plus 1 integer, right? It's here, okay? And you want to calculate going back to here, what is this number is? This is Q1, okay? And this xk, this xk plus 1, the data. And you want to draw a line here, okay? This is the straight line, okay? And you want to have linear interpolation. So linear means you just draw a line there. Instead of a curve, you draw a line. And you try to figure out that what this number is, okay? And how to calculate this number? We'll be using an idea of similar triangle, right? This horizontal alpha over the horizontal 1 will be same as the horizontal of QP minus XK over the horizontal XK plus 1 of my XK. This formula is, okay? And you multiply, cross multiply both sides and move XK to the other side, you get this formula. So that's how we have that formula. Is that okay? Of course, this is just same as what we said here, okay? But it's the linear population, but it's just a division of the data, right? Because mean is the halfway, right? So if you have 0.5, it's only halfway. If you have 0.25, right? How we do it? You get a quarter of this whole distance. That is what it means. Okay? If half would be half of the whole distance. If you have 3.75 would be 3/4 of the whole distance. Okay, that is something, I hope that's not something too difficult. Okay. Is that okay? So maybe example will help, okay? In this example, we have 5 observations. So n plus 1 is n is 5, 5% is 6, okay? Q1 is a quarter of data. Quarter means P is 0.25, okay? So turn out that this 6/4, right, is 1.5. And 1.5, look at the lower end, is 1, right? Because it's actually 1.5. Instead of 3.5, it's 1.5 here. And then this one is 1, and this is 2, right? And this halfway, right? Alpha is 0.5. Halfway of the distance is 1, so it's 1.5. Is that okay for this one? Is that okay? Good. And for Q3, and again, n plus 1, where n is 5, n plus 1 is 6. And because Q3, you look at the third quarter of data, right? The third quarter is 0.75, okay? Times 3/4 will be 4.5. 4.5 means it's between 4 and 5, right? And then halfway of 4 and 5, okay? So it's 4.5. So that's how you get this one. And now you look at 1, 2, 3, 4, 5, 6, okay? You have 6 observations. So n plus 1 will be 7. 7 times a quarter is 1.75. And then the left side is between 1 and 2, okay? And 1.75 is a 0.75 way up to 2. So it's x1 times 0.75 of the distance, okay? So it's 1.75, okay? Similarly, you have 7 observation times 3/4, which is 5.25, which is 5, and then what you drop out is alpha, right? Alpha is the one, is the decimum places, is 0.25, and this is x5 times 0.25 minus the distance will be 5.25, and at the end you calculate the IQR is 3.5, okay? So you can see 3 methods, you end up with 3 different answers, and you want to ask what should we do when you do exercise exam? We'll use method 3. Not because we are picky, but because when there's exists an Excel function, an R function for that. Later you will see. So that's why make our life easier. Okay. And we talk about a linear population. Okay. Actually, there's a mathematical foundation for that. It just later you see there's a uniform drawing a number from here. But anyway, I think that is a intuitively more appealing to use this definition. Okay. Of course, there's some foundation to explain why you use 1 and 2, but we just choose to use the one that having a more intellectually support. Okay, it's a better one. Okay, making more sense. But anyway, Now, before we go to break, in 4 minutes time, I want to talk about variance, which is going to be probably the single most used measure beside mean, right? Because basically the most you can see is the mean, median, skewness, and kurtosis, basically the four of the thing that you would often see, okay? Variance is what, okay? Variance is basically you want to talk about how each data is different from the mean, right? So you can easily imagine that I can calculate for each observation, I calculate the distance from the mean, right? Because it's how far from the mean, right? How dispersed. And then add up all the distance, right? That's the most direct way, right? I'll calculate the mean, okay? For each observation, I calculate distance, okay? Add them up, then we're done, okay? And of course, we want to divide them by number of observation, right? It's average of this distance, okay? It's the mean of the distance from the mean, right? It's very trivial, it's very intuitive, right? Calculate how the data is dispersed. Yes, that means that you, instead of this formula, you'll be doing this formula. Right? Instead of square, you have this absolute value, right? This is the most intuitive, is the average distance from the mean, or average absolute distance from the mean, okay? You will say, okay, this is have a very good intuitive meaning, right? Indeed, this is a very important idea too. So when you do machine learning, this is a very important measure. This is called the average absolute deviation, okay? And variance average square deviation, okay? To calculate distance, okay? And the reason why this is not used is because of mathematical idea of when, I don't know whether you know, if you learn calculus, you learn that actually this absolute distance is not a smooth function, which is not a differentiable function. And when you cannot use calculus to do a lot of stuff. So that makes our life difficult because we know how to do calculus easily, but now without calculus, things are difficult. And that's why before the advent of computer power, this is not very used a lot. So you can see a lot of things, we do a lot of things square. That make our life easier, okay? Because know how to handle square stuff. And that's why now the computer is there, right? We don't do the calculation anymore. We don't need to do it because computer is very fast. So that's why in the recent days, you will see a lot of them are based on this one. You can calculate this one too, because calculator can do it easily. And that's why this is also a important measure too. But we'll follow the tradition, we do the square thing, okay? Because it's most commonly used, okay? And compare this absolute distance and the square one, you will see there's a main difference is this is linear in the sense that if you look at the mean, if you move one observation further from the mean, okay, on the right-hand side, on the other side, you move in closer, okay? This measure will not change, okay? But it will change for the variance. Why? Because the more further away from the mean, once you get square, you expand, right? Because square is a convex function, but anyway, but it's just like the further away, it's getting more important, okay? So that's why in the variance, in a sense that you will be saying that if a lot of data are far away, the variance is large, okay? So I don't know whether good point or bad point, but indeed it's a feature of this measurement, okay? If a lot of data that far away, if a few number of data set, there's a extreme data, the variance explode, okay? Suppose you consider data set that is a lot of data concentrated around the mean, but only a few very far away, the variance can be huge. Compared to the case that is, the data is like slightly away from the mean, okay? Okay? So that means that the variance using a square way is can be expanded by the presence of the outlier. Okay, so this formula, okay, is the distance from the, we'll calculate each observation, look at the distance from the mean, we get it square, and when we get it square doesn't mean that it's on the left and the right the same. Okay, and you can understand why we have the square, because if you don't have the square, it will be 0. Right? We learned that what's the meaning of the mean is exactly the center of the data, right? So that is the meaning of this variance. Okay, I guess I should have a break. I'm sorry for overrun for 2 minutes. We'll resume at 9:30, I guess, by standard. But in the meantime, I'm here to answer the question you might have. Yeah, feel free to walk around. Only it's a break now, so you can have fun until 9:30. Early this morning. Pick up the 6:30. From Ireland, east, so it's like 1 hour something. So we get a school shuttle for the staff. I think have to get all the way to the north. Only for this month. The video like this. I will try to see next class. Everyone has a laptop. They happen to be a laptop. Excel. Hi. Let's get back to the break. Let's come back. Unmute is we resume now. So repeat again the variance. The difference variance is like the distance from the mean, and then we square it, and then add all observation up, and then divided by total number of observations. Okay. And actually, someone asked immediately in the break why I have this guy. Okay. Why I need some adjustment factor. Okay. Actually, I explain here. The sample one is better to use it when you in the real world. We explain later. You multiply by this factor n over n minus 1 is a bigger than 1. Okay. So why you have to multiply something bigger than 1 is because this one will be a better estimate when you use data. Okay. You have a okay, I just want to try to brief idea is like the population. You have the population. You have the population. For a population means the things you want to study. Okay. You want to study. you have itself as a mean and variance, right? Suppose you look at, for example, look at the income of everyone in Hong Kong, okay? There will be a mean of this income. There will be variance of this income, okay? And we want to know these two, okay? Of course, you can ask for every single one, report the income, then you can calculate the variance, right? But in the reality, we can't do that. We will select some people, calculate the mean, okay? And this mean turn out to be a good estimate for the overall, the real mean. That's no problem. So that's why we don't have a sample kind of mean, okay? The mean you calculate from a small sample is a good thing to predict the overall mean, okay? So that's why when we look up the sample, just want to do census, look at the mean, fine. Predict the overall picture would be no problem. But when you look at the small thing, calculate its variance, okay? That turn out to be smaller than what you expect in the whole picture. Because you're only collecting some of the data, then actually you don't capture all the variability of the whole data set. The data set is much more diverse. So you have to adjust by your sample size. The larger the sample, this adjustment factor will be getting smaller, right? This n over n minus 1 is decreasing in n. Okay, suppose n is very large, then this one will be 1, close to 1, right? It's just like this shape, close to 1, right? So when n is very small, then this number will be large, right? So that's why later we explain this adjustment is good when you do prediction, okay? So that's why later we learn next class, hopefully. When Excel spreadsheet, when you say variance, VAR in the Excel, that one automatically by Excel default is the sample counterpart. Okay, that actually they would in Excel actually give you this one. Okay, unless you tell them give me the population one with .p, then you will give you the population one. Okay, so that's the reason why we use it. So of course we will explain that to you in the I think in the 6th week, second half of the class. We'll tell you why this is the good one. Okay, the idea is it's a better use. Okay, so pardon me if I not explain it clearly because it really required to understand a lot to go back to why this makes sense. But I would say to tell you that is because when you try to predict using the data to predict what actually happening, you underestimate. The reason why underestimate because you don't look at everything in the data set, right? So that's why you just pick up something. When you pick up something, then turn out to be likely that you are underestimate. Okay, for example, imagine in this case, if a die, a 6-phase die, you know the number is 1, 2, 3, 4, 5, 6. Okay, of course you have rolled many times, so we see 6 of them, right? And then you expect 1/6 of them is 1, 1/6 of them is 2, and 1/6 of them each outcome appear, right? 1/6 of times, right? Now we just roll several times only. Okay, it's very likely that you may end up with 1, 2, 3, or 1, 5, 1, 3, 5, or 1, 4, 3, right? And in that case, you estimate. You can see when the smaller sample you have. Suppose you just roll 1. Okay, the variance is very small. That's one observation. Just the variance is just 0. If you roll two times, you can be 1/6 or 1/5 or 1/3 or 1/2, right? Then it's more likely that they're closer to each other, right? Even though the range, right? You're underestimating a lot of time because you only pick up a few observations, not the whole picture. So it's likely you underestimate what's going on in the real world. So that's why we would have to multiply to get bigger. Okay, so that's the idea. I hope it makes sense to you. Be sure you ask the question. But sometime, as I said, we have to save the question until the end. It's not the I mean that is I think this is a journey of education. Is there's always some problem you can't solve, or you may have. I mean, the curiosity makes you want to learn a lot. We want to know why it's the case, right? Because in the high school or education, we will want to know everything, right? Try to explain you a consistent picture. But when you go to a college, when you study classes, there's something we can't explain, okay, indeed, or something you require more knowledge to explain. So you have to learn how to live with the problem, how to comfortable yourself to say, something you don't understand, is take it as given. And later, when you learn more, then you know more. And even sometime when I do research, right, there's something I don't know. I mean, that have to be, I don't know. I mean, you have to be happy with something I don't know. This is actually, when I learned this statistics, right? So I have one time I also want to understand this, and the teacher don't explain. And that's why I go to the library. At that time, the internet is not that good. Although library, I actually effectively pick up every textbook from there. It's a free yourself to try to find the answer. Of course, it's sometimes very rewarding, but over several times, then I figure out that it's not worth my time to do it, because every time just pick up every textbook there, then it's very tedious, because not all the textbooks have questions for everything. So we pick up a lot of textbook to figure out. Right? Sometimes it's more advanced and you don't really understand what's going on there, right? So if you have a question about want to know more, I can try to answer you. I'll give you some hints. So especially we have small class, so just feel free to ask, because other class we have double of this class size. So it's not easy to have a small class. So being a small class, it's feel free to ask a question. But I hope you answer a question. The intuition is there. Okay. So give example. This is usually, I think, how you learn in the high school, right? If you ever heard variance. So the data is 1, 2, 3, 4, 5. Okay. List them in the column. Calculate the mean. Okay. It's 3. Okay. Why I list them this way? This is the spreadsheet way. So this is how we actually calculate from scratch when you do Excel. Okay. So so you have the column A is here, column B is here. Okay, I assume you have some idea about spreadsheet, but we'll talk about that later. And this, you do the subtraction, right? Just this minus this column, right? This is the deviation from the mean, what we call, okay? And then you square them, add them up, okay? And divided by 5 is 2, okay? Population is 2. And you divide it by 4, there will be 2.5. So you can see the sample variance is bigger than the population one, because as I said, when you collect a sample, you underestimate, so you have to be bigger. Okay, but as I said, we don't explain why we need to use this, but most of the time when you see the report, they will call the sample variance, sample mean. Okay, but sometimes they ignore the sample, but by default it's a sample. Okay, so if you don't think say any population and sample, actually what you see in the data is almost always a sample one. Okay, so that makes sense of this one. Now, as I said, the variance is the most important one, but sometimes you don't see variance a lot because you will see a lot of them in the other form. It's called SD. Short form is called standard deviation. Okay. One of the drawback when you have the variance is you square it. Okay. When you learn measurement, then the measurement would really depends on how you measure things, because when you measure in meter or centimeter, right, you got square, right? So it become the unit will be not very useful. So that's why you take a square root to remove the problem of unit square, right? Because we talk about measuring meter, okay? And it's square, it becomes square meter, okay? Then what does that mean? It's not very clear. And also we wanted to talk more clear, then we will use standard deviation, okay? And turn out to be this standard deviation will be the key actually for the second half of the semester, okay? A lot of things we rely on this standard deviation. Of course, same as variance, but we rely on this measure, okay? This mean and standard deviation will appear basically the main two things you need for the second half of class, okay? And similarly, there will be sample counterpart, right? Because square root of n over n minus 1, this is the adjustment. Okay, so that's nothing deep, but this measurement will be the key for the second half of the class. So I hope you would get a taste of it. Okay, is that okay? Just take a square root. Okay. Now, the third one is related to this one. It's called coefficient of variation. Okay. If you have one data set, okay, measuring something, and data set is measuring something, okay, and such data set A and B, when I say data set A have higher variance or standard deviation than data set B, right? Then that you're saying that A is has more diverse than the B. Okay, that's no problem. Okay, but sometimes they don't have the same mean. Okay, or they measure in different quantity. Okay, then we care about the how the scaling you're doing. So that's why we divide it by the mean. Okay, so the idea that is trying to compare the idea, say, suppose you want to look at, I don't know, maybe look at suppose to take the exam. Okay, I want to compare how variability of this class compared to other class taught by the other lecture. Okay, maybe our class have higher variance than other class. Okay, but it just may mean that our class have maybe a higher scores, right? If suppose I use the score from 0 to 100, okay, and the other lecturer may be using from 0 to 10, okay. From 0 to 10, the variance can be very small, right? I use the score from 0 to 100, okay, score can be very big. Okay, how to compare two data sets? The idea is to divide them to the mean. When we scale from the mean, okay, divide the mean, then you can easily compare two data sets. Right? That's how you do it. Okay. Or the other way around is I consider, even if I make an exam, okay, I have two parts, multiple choice and non-question. Okay. And I want to see maybe multiple choice is 30%, long question is 70%, right? That's actually what usually the exam is being done. And you want to see, okay, are people getting more correct in one part or the other, right? It's more likely to be more diverse for the MC or to the long question, right? It's more people guessing for multiple choice or more people guessing for the long answer, right? One way to look at is the variance, right? But variance cannot tell too much because one is 30 marks, one is 70 marks, right? So the way to proceed to see which part have more variability is to divide it by the mean. Okay, and usually the standard way also you multiply by 100, just convert to percentage form. Whether you want to multiply 100 or not doesn't really matter, but I think the Excel they do it. But that is something simple, and then the sample counterpart, I just use the sample, so there's nothing deep here. Okay. So maybe do this, right? 1, 2, 3, 4, 5. The sample mean is 3. The variance 2. The sample variance 2.5, right? Standard deviation is square root of 2. Sample version is square root of 2.5. And population will be this number divided by 3. Okay. 47, and this is 15. Oh, sorry, I shouldn't have an equal sign here, but you get what I'm saying. Okay, so there's nothing deep here. So I guess this is something very natural. Now I want to talk about kurtosis and skewness. As I said, skewness is how symmetry data is. Is whether more data on the left-hand side or more data on the right-hand side of the mean. Okay, and kurtosis, looking at the tail, is how the extreme values they are. For those who want to study finance or do the trading, then you want to look carefully about this. Okay, so Actually, the idea of the skewness is somewhat actually similar to the mean, sorry, similar to the variance. Okay. Don't look at the denominator, look at the numerator. Okay. What numerator looks like? What does it remind you? Maybe I try to be more interactive because it's early in the morning. People are sleepy, but do you remind you something? The numerator looks like what? If the 3 become 2, it is a variance, right? Variance raised to the power 2. Okay. Now we can see raised to the power 3. What happened? When you power 2, it doesn't matter is on the left and the right because square, negative number, square become positive number. Okay. It's always positive number. Okay. So that's why variance is always bigger than 0. Now you have 3. Okay. With the power 3, it means that on the left, you raise the power 3, still negative. Positive, it will be still positive. Okay. So you may cancel out. So if the data is nicely symmetric, okay, say 1, 2, 3, 4, 5, okay, and in that case, they will cancel out, right? 1 and 5, that want to cancel out, right? 2 and 3 cancel out. Those 1, 2, and 4 cancel out, right? So if perfect symmetric with power 3, they cancel out. Okay, so that's why you raise the power 3. Okay, and why this is the numerator? Okay, just as variance, but not raised to the power 2, but raised to the power 3. So that's why left and right will make a lot of sense. Okay, it means that you have a observation is way further away from the mean, then we will expand like crazy because raised to the power 3. And okay, then you notice why we have to divide the denominator by standard deviation. Okay, it's because we only want to measure how the skew the data is, right? It's whether more left and right. You don't want it to be affected by how variability of the data. We only want to measure that. That's why I scale it back down a little bit. Okay, so the denominator is not necessary. Okay, the numerator is a key. The denominator is just the way to try to avoid your skewness being expand a lot because of data is so varies. Okay, but otherwise it's just a simple measure. Okay, so so when you do this, this will become like something like this. Looks humongous, crazy thing. Okay, but turn out you when you do Excel spreadsheet or when you do our programming, that one will be intuitive. Okay, so what you need to do is understand this idea, right? And remember this formula, and that will be fine. Okay. And as I said, if you're perfectly symmetric, in the case it's median to the mean, it's a very nice thing. It's a single shape, it's bell shape, right? Then the left both sides would cancel out. Okay. And if you have the data on the, this is the right hand side. It's a lot of data on the right hand side, right? Then because raised to the power 3, so the further away from this, right? Then you much bigger. So there will be positive skew, and you have the left, a lot left, then will be negative skew. Okay, so so this one is very technical. Okay, we don't prove it, but what I try to say that is when you do the sample counterpart, actually you multiply by some very weird stuff. Okay, again, this will be bigger than 1. You can easily check. Okay, for those who know math, it's easy to check this bigger than 1, but I'm not going to talk about that. But why you have to multiply by that? Again, the same idea of variance is you underestimate the skewness of the data when you try to collect data from the sample. Okay, so but I'm not going to go to detail why. The reason why is because this is what you see from the Excel. When you calculate skew from the Excel or R, this is what you have. You are not getting the blue one. Okay, if you want to get the blue one, you have to calculate from scratch by yourself. What you get from the Excel spreadsheet or package software package is always this guy. So it's the one you calculate intuitively, multiplied by this adjustment factor. Is that clear what I'm saying? So I claim is the meaning of the theoretical meaning is this guy, which we know have a nice interpretation, okay? But when you're actually using them to estimate what's going on there, you have to, you use the more complicated one, multiplied by something very weird stuff. As I said, I'm not going to explain why we have multiplied very weird stuff. It's beyond our scope, but we can explain later in the second half of this course why we have to do this adjustment. Okay, but we're not going to explain this one. But this is something is like better measure. Okay, you can imagine that this is if you don't want to think about the math, you can imagine that it's experience tells us that this is a better measurement, better estimate. Okay, I think just like everyone play basketball, right? At least know basketball, right? And I'm not expert, but I know the rule, right? There's a basketball, right? There's maybe correct me if I'm wrong, but a basketball. I mean, sorry for my drawing, right? This is the basketball, the board, right? So how can you throw in the ball? Okay, unless you are expert, right? You may get inside the ball, go inside the hole, right? But if you are not so expert, what you're doing to make sure that you are in is to, yeah, right, is to, yeah, you can tell what's there. Right, so you have to, get in, you have to aim the other direction. You cannot aim directly. Same idea here. If you want to guess it, you cannot just directly get what it is, you have to get it the other way around. I hope that makes sense. Just, I think it's a good analog, but so as I said, pardon me, I'm not going to go to detail for technical. So just, this is the one, okay? So this is how you do it from scratch from the spreadsheet. So we have 5 data point, 1, 2, 3, 4, 5. And the mean is 3. Okay, there's nothing new here. And you calculate the deviation from the mean. So 1 minus 3 is minus 2, 2 minus 3 is minus 1. So this is the column. And you square it, right? Everything is positive. You take the cubic, it will become negative A. Okay, negative 1 and 0 and 1A. So this one is symmetric. So we expect this is 0, which is what we expect. Okay, and the sample standard deviation is 10 over 5 minus 1. Okay, 2.5. This is the standard deviation, sample standard deviation. And skewness, regardless of sample 1 or population 1, is all 0 because symmetric, as expect. Okay, so the other example here, which is a skew one. So skew one will look like this. Okay, this graph only draw because only a bell-shaped one, but in the real world can be multiple bell there. Okay, need not be like this, but this is just idea of it doesn't imply this. Okay, only when you talk about bell shape, this is a graph. Okay, and the other example is we have a data which is skewed in the sense that the last data is not 5 but 10. You can imagine that it's more on the right hand side, more on the positive is like. But let's see whether this is the measure we get is what we want. Okay, so 1, 2, 3, 4, 10. Tell the mean, add them up is 20. 20 divided by 5 is 4. Okay, so that's why the mean is 4. Okay, and you subtract each observation by mean, right? It's -3, -2, -1, 0, and 6. Okay, some of them is 0 as we expect because standard data, right? And you square each observation, -3.9, 4, 1, 36. This is, add them up, is 50. Okay, and if you take the power 3, then it's the negative. All right, so it's 180. So you can calculate the sample variance is 50 over 4 because n minus 1, 12.5. Take a square root is 3 point something. Okay, now we are ready to calculate. Population 1 will be is the mean of this guy, okay? Because the formula is this one, if you remember. Sum of the cubic distance over n, okay? And this is the sum of the square distance over n, okay? So sum of cubic distance 0 over 5, okay? And sum of cubic distance was 10 over 5. Take the square root of 5 over 2. Oh, sorry. We're going this one, okay? 180 over 5, okay? And we have 50 over 5. Take the to the power 3 over 2. Okay? So it's 1.138. Okay? And now when we have this sample one, it will be more complicated. Remember the formula here is we use this one, n over n minus 1 times n minus 2, and sum of this over the standard deviation over 3. Okay, so we use this formula. N over n minus 1 times n minus 2, so there will be n minus 1, n minus 2. Oh, sorry, this one. Okay, and 180 is this guy. Okay, over this sample SD to the raised to power 3. So this is the answer. So you put in the Excel, this automatically gives you this 1.69397. Okay. And you can easily see the sample one is much bigger than the population one. So, and actually you would expect this one is a better measure. Okay. Is that okay? Just saying that it's a skew on the other side. Any question? If no, then I hope that is clear. If positive skew, then it means that there are a lot of data here. Okay. And actually, if you why positive skew, because when you try to draw the line of symmetry, something like here. Okay, that's why it's skew on the positive. But that's the English meaning why positive skew. Because the line of symmetry is okay. No, it's on this side because it's flipped on my side. Okay. Okay. So I hope that will be clear. Negative skew is idea the same. It's just like the data, if you try to draw the line of symmetry, something like this. That's why it's like this. Okay. But that's the idea. So last one we want to mention is the skewness. Okay. You can easily see the skewness is so similar to what we see the kurtosis is very similar to the skewness, right? Instead of look at the numerator, instead of raising to the power 3, you raise to the power 4. The numerator, of course, normalized, you just raise to the power 4. Okay, to make it unionist, right? Because you see the skewness and the kurtosis, that thing has no unit. Okay, it's not affected by the measurement. You measure data in cm or m with the same thing. Doesn't reflect the measurement, doesn't make a difference. So then look at the numerator because this only thing is important because the kurtosis is the numerator is just like we scale the thing to compare data. And it's raised to power 4. Okay, why do we do that? Okay, what's the meaning of that? So if you raise the power 4, it means that on the left of the mean, so left is this side, right? Left of your mean and right of your mean is positive, right? Because raised to the square and square, but negative is gone. Okay, and you compare to the variance, what's the difference, right? It seems like there's no difference from the mean, no difference from the variance because variance is square. You just make it 4 times. So what is the deal here? Okay, it actually means that when you are very far away from the mean, it will be even bigger. Okay, and that means that if the data has a lot of extreme value, raised to the power 4, it will be big. Okay, then the question you may in your mind is why 4? Why not 6? Why not 8? 100, right? So that's a very easy way to figure out. Of course, 4 is the thing that can do the job. And later, actually, a more technical idea would be saying that not all distribution may have kurtosis. So this is a raised to the power 4. When you have some later you learn distribution, then actually some distribution may not have more than 5, 6, or 7. So it's for some distribution you can define skewness. You may not have kurtosis. Okay, actually, for technical people, actually they say even variance may not be defined. So every distribution may have mean. Okay, mean is no problem, but may have variance is not finite. Okay, can be not finite because it can be distributed from negative infinity to positive infinity, and may not have well-defined the skewness, may not be have well-defined kurtosis. So that's why the lower the power, the better, because it will apply to many things. But anyway, if you talk about from the machine learning world, there's no harm to talk about 5 or 6 or 7 or 8 or 9, doesn't really matter, right? Why don't we do skewness is 5? It's fine, it's no problem. But we know it just satisfy our need. Okay. For skewness, actually you can do 5th degree. Okay. But you have higher power, then your data is less precise, right? Because you are also computationally more demanding, right? The computer can easily raise to the power 5, but it can become increasingly inaccurate. Although the computer is very good, but still, when you raise the power, usually the computer doesn't work very well. Okay, so just raise as little as we want. Okay, so this is with the power 4. It means that the data that way further away will got a lot of power because with the power 4, right? So and the good thing about this is later we learn actually we call excess kurtosis. Okay. Usually we don't report the kurtosis by itself. We report excess kurtosis, which is minus 3. Okay. Why this special 3 here? Okay. The reason is the standard thing you learn is the bell shape, what we call the normal distribution or Gaussian distribution, which we'll be using this for the second half of the class all the time, which is called the normal distribution. And called normal because it appears a lot of time is normal, right? That's why you learn if you're born in the age of IM, right? A, B, C, D, E, there's what we call the bell curving, right? This group of people get A minus and B and C and D and so on and so forth, right? The bell shape curve. Or the IQ is following the bell shape, or the height is following the bell shape, the weight is following the bell shape. A lot of things are following the bell shape. Okay? So that's why the reason why a lot of things following bell shape is very important theorem we'll cover in the middle of a semester is what we call the central limit theorem, which said if your measurement is coming out from many random process, okay, turn out what you get is a bell-shaped curve. Okay, IQ is a combination of so many things. Your nature, your nurture, how you study, whether you play a lot of time, that you got IQ. Also the height, right? Depend your mom, your dad, your grandma, your grandpa, your environment, what you eat, what water you drink, that at the end, or DNA at the end, the random mutation end up your height and your weight. So this, when the things are determined by a lot of random stuff, it's a normal distribution, right? Look at the trees, look at the size of leaf, look at the size of apple, right? Everything is a normal distribution. So that's why when we want to compare whether things have extremely large ends, we're going to compare to the normal distribution. And normal distribution, we'll calculate, we don't prove it, but you can try to do it by yourself, is normal distribution have kurtosis of 3. Okay, so that's why when you try to compare the data, what you get is whether you have extreme tails or not, is minus 3. If more than 3, it's bigger than the bell shape, then it's not so good in sense of a lot of rare event. But if it's less than 3, that's good. Okay, that's the idea. If exactly if it's normal. Okay, so that's why we have some greed, I think greed or Roman, I think it's Roman, or greed, I think it's Roman, I don't forget. So it's Mesocratic, Leptocratic, and Platocratic. But anyway, I don't think you need to remember all this, but turn out to be just mean the fat tail and thin tail. Okay. I'm not expecting you to remember this greed, whatever thing, but they are using in the literature or read the textbook. They mention that, so that's why better let you know. It's not very important because now you have Wikipedia or Google. Whenever you don't know, just look at the Wikipedia. Okay, but you have to understand. Usually, what we report is excess kurtosis because excess sometimes is not mentioned. So, but you always compare to the normal one. Okay, and you may ask why we care about all this thing. It's normal, and this is, you can see this is thinner. This is fatter. The blue one actually is a normal. Okay, it's like, okay. And again, there's a crazy thing here goes on. Now this sample counterpart is a very complicated object, not just a multiplying thing, but you have to subtract again. Okay, so this is a humongous object. It's a beyond our imagination. Why this makes sense, we don't explain. Okay, we put it here because this is, if you want to calculate from scratch, okay, and you want to compare your answer to Excel, this is what you have to do. Okay, you have to do this crazy thing. Okay, lucky I told you Excel gives you this answer directly. Okay, but if you really want to compare what you see and whether you make sense of the Excel spreadsheet, then that's what we have. Okay, and okay, and we are trying to play around again for this one. 1, 2, 3, 4, 5. Okay, in the mean, this calculate difference of this. I think this up to the first 4 columns we know very well. The last column is also fine, just raise to the square again. Okay, it gives you 34. Okay, so that's why the answer is 34 over 5 over this one. This kurtosis is 1.7. Okay, the excess kurtosis, okay, is negative. You can imagine because this is a triangular shape. Triangular shape, of course, have a much thinner tail than the bell shape. Okay, so that's not something surprising. It's not, there has no extreme risk. And sample kurtosis is this formula. I think I can left you for try to apply this formula to here. Okay, just replace n plus 1, n minus 1, n minus 2. Okay, and this is 34 coming from here. This formula here, right? This sample 2.5 square, you see it. Okay, and minus 3 of this guy. I think you're okay to do that. Okay, so I don't think I need to talk about here. Okay, and why this formula is correct is beyond our class, but this is what we have. Okay, and this is what you get when you do Excel spreadsheet or you do our program later. We learn this is give you this one. Okay. And you can see when you raise the power 4 already, it becomes very big object. Okay, you can imagine that if you raise the power 6 or 8, then your computer will complain. Okay, so that's why we keep it manageable, right? Raise the power 4. Okay, and I'm not going to go over the detail, but you can see. Oh, sorry, this should be 15. Sorry, typo here should be 15 because the data is 15. 15 here, and you will see the population one, you calculate is very small, but when you have the sample one, which is much larger. Okay, so that's exactly what we said when you calculate the thing that is underestimated a lot. Okay, so you have to use the sample one. But anyway, I guess it's okay. Any question? Any question? This part? Okay. So why we care about kurtosis is about extreme value. As I said, there's a financial bubble is underestimated. The extreme risk, the insurance is large scale, and income we talk about income inequality. Why I care about that? So at the end, I want to talk about variance and correlation coefficient. I guess last 3 minutes, I think it's okay to get at least give you some idea why we care about this too. Okay. And this is actually deviate from what we said. It's just like before we only have measurement on one dimension, that's X. Observation, we call it the mean, median, mode, or variance, kurtosis, or skewness. Okay. Now, instead of observation of one attribute, we have two attributes. Okay. Say for single one, we not only asking his income, maybe also asking his education. Okay. This is a known now. This is the most random regression analysis by economists. Okay. They try to and also very important is to understand how education affects your earning. Right. That's why you're here instead of making money. Right. Why you spend the time and money in school. Right. And the first study is trying to see, at least you want to see is people graduate from college earn more. Right. At least you're trying to. So the first thing is whether those people actually earn more. Right. The immediate answer is maybe yes or no. Right. I don't know, but that is something we want to see now. And the idea is we are calculating the covariance and correlation coefficient. And covariance we see is, by the name suggests, is very similar to the idea of variance. Okay, let's go directly the definition. Okay, the definition you will see is for each observation, we have a pair one. You have x1, y1, which means that for one object, for one subject, you'll be having a two attribute, x and y. As I said, it's income, education. Okay, or for business application, you may see x can be, maybe you can easily think you are a food store owner. X may be money he spent on his food. Y may be money he spent on his drinks. Okay, then you want to see whether people who spend more on his food and also spend more on drinks, right? If they do, then you may want to make a special menu, that combo menu that combine the two, or one way or the other, right? Okay, it depends. If they don't, if a negative rated, then you can increase the price of both, right? It's either complement or substitute if you learn economics. But anyway, observation of two things, you want to see whether they move together above mean and below mean. Okay, this is what this equation said. Okay, this, if you replace this guy by x, right? Actually, this is a variance, right? If y and x actually the same thing, this is a variance. Okay, but we are looking at this. We're looking at x and y at different times. Okay, just when x is above the mean, y is above the mean, then it's positive. If they below the mean at the same time, they're negative. Okay, if one above the mean, one below the mean, then the multiply will be a negative one. Okay, so if they always move above the mean and below the mean, it'll be a positive measure. If other one, will be negative. Okay, so that's why look at whether it's positive, they move together. If negative, they move oppositely. Okay, and you divide by n. And similarly, you have n-1. Okay, but I guess I should stop here because I think time's up. So we will be talking remaining thing next class, and depends on whether you have a computer view, we can cover Excel and R for the next class. I guess I should end here. So see you next week. Have a nice day. So we'll end on you. So if you have any question, you can send me an email.
Thank you.
Thank you. So if you can, try to bring the Excel, try to bring your computer if possible. But if not, then we can just wait until the lab section.
I will try to check next class whether you bring it.